Okay, so today we are going to be talking about airfoil shape and aircraft stability. And there was a question on Monday whether we can give more examples of what might appear in the quiz. Right. So today I'm going to first give you a few examples of what the type of things that might appear in quiz regarding thin airfoil theory. Okay. So for example, here is a question I think that would be just testing one aspect of thin airfoil theory, right? So basically I'm overlaying the X-foil calculation of 3 different airfoils. Basically they are all symmetric except for one is super thin, the other is moderately thin, and the third one is thicker. And also, well, this is apparently from kind of 3 pictures stacked on top of each other, right? So the question is ask you to identify, okay, which pressure distribution belongs to which airfoil. All of these are at 5 degrees angle of attack. Any ideas of what to use? Yes?
I think like when it's more like
Sharp?
yeah, sharp, it should have like more pressure when it's like around. So I feel like it should be more like
Spiky?
yeah.
That's completely correct. So one aspect of thin airfoil theory also regards to in what kind of scenario it is not correct, right? So thin airfoil theory assumes that the induced flow from the vortices placed inside of the airfoil is much smaller compared to the free stream, which is not going to be correct around the leading edge. And as a result of that, if you look at thin airfoil theory prediction, the pressure spike or the distribution of vorticity actually has infinite concentration around the leading edge. And as a result of that, the amount of vorticity at a certain location corresponds to how much pressure difference is on the upper and lower surface, right? So infinite concentration of vortices means infinite pressure difference, right? Which also means the low pressure side is going to spike to infinity, which is never going to happen. And exactly in what region it is wrong actually depends on how thick the airfoil is. So for a thin airfoil, it is only wrong for a tiny region, and the pressure actually spikes to pretty high values. The thicker the airfoil, actually the rounder the leading edges, the more blunt the leading edges, there is a bigger region for which thin airfoil theory is not correct. And so basically, if you look at this corresponds to the thinnest airfoil, this one, the moderate spike, corresponds to the medium airfoil, and the lowest spike corresponds to the thickest airfoil. You have a question?
So it's basically assessing the ability for the pressure to dissipate from the stagnation point at the very front of the airfoil. So if it's very sharp, it all builds up right here, versus if it's round, it allows the pressure to dissipate in a way, and so it's not as much of a spike.
Yeah, you can think of that way either.
Sure.
I mean, another way of thinking about it is something we'll talk about, I think, probably on Friday. That is another way of looking at the pressure. That's basically, we already studied how we can think about the pressure in terms of Bernoulli's principle, right? So basically, if the velocity is high, the pressure is going to be low. Another way to think about the pressure is the pressure providing centripetal force. Okay, so if you have a sharp leading edge, the velocity, the flow has to turn very sharply with a small radius over here. That actually necessitates a low pressure at that location to provide enough centripetal force for the flow to actually turn for the small radius. Yes?
Can I ask just, when you say it's incorrect, I understand mathematically it's incorrect, but in real life we still experience the suction peak and we still have this behavior. Just is it like
it's just not as high, right? So if you look at this, it's pretty clear the more blunt leading edge, the pressure peak is only like less than -2 in CP. And the medium one has like -2.5, and the thinnest one, actually don't know how much it spikes to, but like yeah, lower than -5.
Okay. But then wouldn't the blunt one be, I guess, somewhat correct because it doesn't like go to infinity? It just stays somewhat low? Or no?
Yes. Basically, if you compare this against what we looked at previously, the thin airfoil theory calculations. For the symmetric airfoil, you are only changing the angle of attack term, right? So you're gonna see a pressure suction peak that goes to infinity at the leading edge.
Right.
And the thicker the airfoil is, the sooner or the further away from the leading edge, the actual pressure distribution is going to deviate from this one.
Okay.
Right, so you go back to here. Yeah, for the thicker airfoil, the pressure deviates earlier. For the thinner, it deviates closer to the leading edge.
Thank you.
Another thing is what we saw on the on thin airfoil theory. It only prescribes the vorticity distribution. Only prescribes the difference between the upper and lower surface, right? So if you look at downstream, the difference between the upper and lower surfaces should be the same, should be pretty much the same for all of these airfoils. That can also guide you towards which one corresponds to which one for the lower surface, right? We just said that which one corresponds to which one on the upper surface can be seen from the leading edge pressure suction, right? Now, if you think about the difference being the same, then the upper one on the upper surface corresponds to the thick one, which also means the upper one on the lower surface corresponds to the thick airfoil. And the medium one corresponds to the medium airfoil, and the lower one corresponds to the thin airfoil, right? So basically, this are the three different airfoils. Okay, any questions on that? That's one example. And another example, okay, how does the angle of attack change the distribution of velocity and pressure? Okay, so can you, I'm just providing one airfoil, pretty thin, right? And we have calculated the three different angles of attack. In X-foil, if you do ASEC, like angle of attack sequence, you're going to get a plot like this. Okay, so the question is, okay, can you manually sketch the pressure distribution at 3 degrees angle of attack? Here, we only plotted 0 degrees, 1 degree, 2 degrees, right? Okay, so can you roughly sketch what the 3 degree angle of attack pressure distribution is? And also estimate the lift and the moment coefficients. I think we already looked at a similar question of estimating the lift and moment coefficients, right? The moment coefficient shouldn't change as you change the angle of attack, right? So here, because the airfoil is not exactly infinitely thin, it does change, but like almost not changing, right? So your estimate is probably going to, okay, my moment coefficient is going to be the same as this. Lift coefficient, you should see that it basically goes up at a linear rate, and the linear rate is going to be very close to 2 pi. So you can estimate the lift coefficient according to that 2 pi linear rate. But the more difficult one is how do you sketch the pressure distribution? Any ideas of how to do that? Yes? Yes, it's going to peak higher, right?
And then it'll still come down a little bit above.
Mm-hmm.
And then it'll come and peak on like the right hand side of the same area. And then it will be lower.
It'll be lower on the lower surface, right? That's very good. So the first thing I think you should be able to see from this graph is which line corresponds to 0 degrees, which one corresponds to 1 degree, which one corresponds to 2 degrees. Any ideas? No, you probably can answer that because you can estimate what is 3 degrees. Anybody else tell me, like, what is 0 degree, what is 1, what is 2 degrees? at 0 degree angle of attack, what is the difference between upper and lower surface? No difference, right? For symmetric airfoil, for non-symmetric airfoil, that's not the case. But for symmetric airfoil, because of the symmetry, there should be no difference on the upper and lower surface if your angle of attack is 0. The whole problem is symmetric. Okay? And you're going to get the middle pressure distribution. Okay, and why it is middle? Because as you change the angle of attack, as you increase or decrease the angle of attack, the upper and lower surface pressure distribution widens, right? And the amount of widening is going to be linear to the angle of attack, right? That's the A0 term. And the difference between upper and lower surface should have a shape that actually looks very much like this one, except for right at the leading edge. So that's what you see here, right? The middle one corresponds to 0 degrees angle of attack, and this corresponds to 1 degree, and that corresponds to 2 degrees. And the 3 degrees, you add you add basically the same thing as you change the angle of attack for 1 more degree. So you almost linearly extrapolate, right? Basically have the gap between the line you draw and the uppermost line. The gap should be the same as the gap between these two lines. And for the lower surface, the gap between your line and the lowest line should be the same as the gap between the two lowest lines. Okay, does that make sense? That's how you would draw the pressure distribution. Let's go to another example. Any questions on these two examples? Okay. Oh yeah, let me talk about this first before I go to the next example. So,
One question.
yes.
If you were to estimate the lift and moment coefficients, CM wouldn't change with angle of attack.
That's
and
right.
CL you could do 2 pi times d alpha.
Yes.
So that would get your DCL. And then
Yes.
you add that onto.
Yes, that's right. That's right. Yeah. Okay, so we discussed briefly on the NACA 4-digit airfoils last Friday when we play with X-foil, but here we want to connect it to thin airfoil theory. So the NACA 4-digit airfoil is really have 3 parameters. The first digit is the first parameter, I call it M. The second digit is the second parameter, I call it P. And the third and fourth digit are actually the same parameter, I call it T. T is thickness, right? So for example, this corresponds to NACA 2412, right? 2412. That's the designation of this airfoil, and I draw it in green. Okay, so here I completely ignored the thickness. Like when you change this, only the shape changes. I didn't calculate. I didn't take into consideration at all. So basically, it is assumed to be a thin airfoil. Okay, and I have the angle of attack here. So what's important here is that there is the shape of the airfoil. The shape of the camber line is calculated by this formula. I mean, it's not exactly a simple formula. You can see like it has a bunch of things, but you don't have to understand the formula at all. The only thing to understand is that this formula actually gives you a slope of the camber line that's straight in 2 segments, right? So the black line is the slope of the camber. Is it clear what I mean? Like the slope is positive over here because at the leading edge the camber goes up, right? And at this point, point 4 corresponds to P. So P, the second digit, is in tenth. Where is the most camber? Like the highest point of the camber. So, of course, when you are at the highest point of the camber, if you studied calculus, you're going to know the tangent or the slope should be exactly 0, right? So that is why when you look at the slope, it goes linearly from a positive value to exactly 0 at 40% of the chord. and then it goes back at another linear slope all the way back to the trailing edge. So if you just change the second number p, you are basically adjusting where this slope achieves 0. So if you make p equal to 1, it goes to 0 very early at the 10th of the chord. If you, I'm not changing p. If you make it 9, then you're going to see this slope goes to 0 at the 90% of the chord. And if you make it half, the camber goes to 0. I mean, the slope of the camber goes to 0 at half chord, which means the whole slope is a single linear line. So in that case, what is the camber like? What function? It's a parabola, exactly. So the integral of a linear function, of course, is a parabola. All right. So this is if you make the angle of attack also equal to 0. This is exactly what we talked about in thin airfoil theory. It only has a A1 term. So here I actually, in order to calculate this, I actually calculated my A0, A1, etc. And in this case, if I have a NACA, whatever 5, whatever, according to thin airfoil theory, there is only one non-zero number in this A series. That's the A1 term, and you should expect your vorticity distribution to be symmetric, and the center of lift is right at the half chord. Right. So that's a special case for the NACA airfoil theories, and P equal to 4 is actually the most commonly used airfoil, and you have these 2 straight segments. Okay. Right. So, and in this case, like, none of my A's are going to be 0. So all of my A's are going to have a value. I stopped at A5. Basically, the further you go, the less influence these coefficients are to the overall distribution. So I only kept 6 terms, right, in this approximation. If you keep more terms, it'll be more accurate. But like this is, yeah, what I do. So you can use this. You can find the link in the OneNote notebook, and I believe I now synced it, so you should be able to see what is there for last lecture, right? So so you can play with this to see what the NACA 4 digits are going to be affecting the vorticity distribution. So there is one of these questions is the following. So if I have a NACA 5504, so 04 means the thickness is 4%, very thin, right? So you expect the thin airfoil theory to be pretty good in this case. And the second digit is 5, which means the camber is a parabola, right? And the first 5 means just means the at the most camber point, the amount of camber, which is basically how this point deviates from the line that connects the leading edge to the trailing edge, is 5% of the chord length. Okay, so that's what the airfoil is. The question is, can you estimate the moment coefficient around the quarter chord at these 3 angles of attack? Well, I didn't say that because I was assuming you already know at this point the moment coefficient according to thin airfoil theory does not depend on angle of attack, right? So just based on what is here, can we estimate what that moment coefficient actually is? Well, I mean, you actually have multiple ways of solving this question. I mean, one of the brute force ways is to do like the geometric stuff you did on the whiteboard. Another, and to actually divide this shape into many segments and calculate, okay, how much lift each segment has, and multiply it with the leg and do an integral, right? So of course you can do that, but like you get the right answer, and I'll give you marks on that. But like it'll take a lot of time. So a smarter way is to actually use thin airfoil theory, and the fact that for a parabolic shaped airfoil, the lift actually exactly acts over here, right? So for example, if you just take any so at Okay, so at a 0-degree angle of attack, the lift acts exactly over here. So you should take the alpha 0 case. And if CL is 0.6507, which means that there is a lift of 0.6507 over here, you multiply this with the lag relative to the quarter chord, which is a quarter, you get the moment coefficient. So the moment coefficient it should be exactly 1/4 of this. And I think I can move this away. Yeah, and the sign is negative because a positive y moment is nose up, and this is a nose down moment. So this guy should be roughly a quarter of this, right? Which, yeah, it is good up to the accuracy of thin airfoil theory, which is what you expect over here. Okay, any questions? Yes?
So CP equals 1/4 minus CL over CM, or CM over CL.
Yes, the center of lift, that's right.
What is the equation you're using there? It's like when you took a quarter of the CL.
Yeah, so the center of lift, center of lift is equal to a quarter minus my CM over CL, right?
Yeah.
Okay, and in this case, I know it is at 12 at 0 degrees angle of attack, like at half chord,
Sure.
right? So that basically tells me that if I just move the yeah, so basically if I move around the terms, I move this to the left side of the equation and move the half to the right side of the equation, what I get is CM over CL is going to be equal to a quarter minus a half, right?
Sure.
Which is equal to minus a quarter. So my CM is going to be minus a quarter times my CL, which is something like that.
I see. So you intuitively knew the center of lift and then was able to solve it recursively.
Yes, yes. Like the center of lift is just from the fact that for parabolic airfoil, for parabolic camber with 0 angle of attack, the lift acts on the half chord. Yeah, and if you look at the gap between the upper and lower surface, right? This gap over here, it is quite elliptical. I'm not saying the whole shape is elliptical, but the gap between the upper and lower surface is quite elliptical. All right. So that's basically the effect of the A1 term in thin airfoil theory. Questions? So you are discussing.
Yeah, I think I just wanted to confirm how you knew it was negative.
How do I know it's negative?
So
So
you don't use that equation there. Like you can get the negative from the center of lift equation.
Yeah.
But if you were just like calculating the moment based off of like lift and the force across the distance, how did you know it was?
yeah, I'm gonna tell you how I know intuitively the moment is negative. So when we are calculating moment, we are always calculating moment around this point, right? Quarter chord. I mean that's why there is a quarter minus here, right? That's so a nose. So in this axis in aerodynamics, the convention is x points downstream and the z points up. So if you use right-hand rule, you should have x, y, z, right? Z should point up, x should be the initial direction, y should be the second direction. That means y actually points into the board, right? Okay, and a positive y moment is a moment that nose up and mid chord down, like trailing edge down, leading edge up. But in this case, the center of lift acts on the mid chord, so it's actually relative to the quarter chord. It actually makes the trailing edge up, nose down. So it's negative in that sense. Okay, any other questions? Okay, so today we're going to be, there's another one. Okay, can you estimate the center of lift at 3 degrees angle of attack? So basically, here I gave you, at the 3 angles of attack. So basically, I gave you the CL and CM at 0 degrees angle of attack. I think this is a very similar question as we went through in class, right? So basically, you copy the CM at the other two angles of attack and use the formula of 1/4 minus CM over CL to calculate the center of lift, right? And don't be alarmed if the center of lift lies outside of the airfoil, because that is completely possible. All right. Okay. Today we are going to spend the rest of the time talking about how airfoil impacts airplane stability. So a week, maybe more than a week ago, we discussed how like the wings and the horizontal tails affect airplane stability. So at that time, we have basically assumed that the lift always works at the quarter chord, right? Which now we know is not the case. So basically, we're going to revisit airplane stability in the context of a non-symmetrical airfoil, for which the center of lift does not act on the quarter chord. So this is actually a CFD calculation of an airplane like this, basically just a single wing. And the two different cases are, one is the wing is not double 12, a symmetric one, and another one is a 4/4-12, a cambered airfoil. And here I have a CL. Basically, if I pitch the airplane at different angle of attack, I'm going to increase my CL, right? I also know what is the center of lift from nose. So for the symmetric airfoil, there is a little bit of change because like the thin airfoil theory is not going to be exact, and the fuselage actually isn't exactly providing zero moment, right? There is some force on the fuselage, but you're going to see that what we predict from thin airfoil theory is actually pretty. It's not that wrong in the sense that the center of lift from nose doesn't change that much, all the way as you change the CL from 0.1 to 1.2, right? Okay, so it shifts slightly. Well, this is actually, I think what I plotted is just to ignore the negative sign. So the center of lift from nose is actually downstream of the nose. It's basically, you're going to see the center of lift shifts slightly towards the nose, right? So, shift actually slightly away from the nose as we increase the lift. So what does that imply for airplane stability? If you hit a gust, right, of let's say upward gust, you basically have more lift, and that more lift is actually further away from the nose. What does that mean? More downstream.
More moment?
Hmm?
More moment?
Yeah, more moment regarding to the nose, but is that important, right? So where would you want the moment to be calculated when you look at the stability? You want to look at the center of weight, right, or center of gravity. Okay, right? So, and for example, if the airplane flies in equilibrium at 0.5 CL, then you are gonna be, the center of gravity has to be at this point, at minus, let's say, at 2.1. Okay, now as you hit an upward gust, your center of lift shifts towards the tail to some larger distance from the nose. Does that pitch your airplane up or down? Your lift shifts towards the tail, the airplane pitches down, right? That reduces the angle of attack and make your airplane stable. On the other hand, if you look at, if I use a 4/4-12 airfoil, nothing else changed. The airplane looks almost exactly the same, right? Especially from this angle. If you look from sideways, it'll look different. But the stability is very different. If the airplane flies in equilibrium at 0.5 CL, then the center of gravity has to be placed a little bit further from the nose. And if you hit an upward gust, the center of lift actually shifts towards the nose, right? Shifts towards the nose means shift forward. So your airplane is going to have a pitch angle. It's going to have a moment that pitches the airplane further nose up. Okay, that's an unstable scenario. Okay, so you would really want to have a design, right? Unless you have very high frequency active control loss implemented and you trust it 100%, you would really want an airplane whose center of lift shifts towards the tail as you increase the lift coefficient. Okay. And so just to give you a little bit more taste, where do I have? Right. Okay. So if I now get an airplane that's with the, so if I add onto the unstable airplane a horizontal tail, I'm changing this orange curve into the green curve. Okay, so essentially now here you see that if I only have a symmetric airfoil as a single wing, right, it's almost neutrally stable. And if I have just the 4412 as a wing, it's unstable. Now if I have a 4412 with a horizontal tail, it's now stable. So why is that the case? And here, let's actually do a little bit of a math using thin foil theory to figure that out. Okay, so basically I have the 4412 over here, and I gave you at 0 angle of attack what is CL, what is CM. Okay, and the double 12, of course, well, it's all 0 at 0 angle of attack. So now based on these numbers plus thin foil theory, estimate the center of lift for both airfoils at CL 0.4 and 0.5. Okay, and answer the question of are they stable basically tells you, basically is the question, okay, as the lift coefficient goes up, does the center of lift move towards the tail or move towards the nose? If you move towards the tail, it's stable. If the center of lift moves towards the nose, it's unstable. And then estimate both at negative CL. So then the question becomes, are they stable when the airplane is flying upside down, right? Okay. And the third question is, now suppose the symmetric one is placed one chord length behind the asymmetric airfoil. So suppose the two chords are actually the same and span are the same, and the symmetric one is placed one chord length. The leading edge of the symmetric airfoil is placed one chord length downstream of the trailing edge of the cambered airfoil. Okay, and now again consider an average CL of 0.4 and 0.5. Where is the center of lift and is it stable? All right, please come up and try to solve these problems. Here you go. What happened? Okay. Okay. Yeah. Box here. Let me turn on lights. Just came? Okay, so the question is, if I only have this airfoil as my wing, estimate the center of lift for CL equal to 0.4 and CL equal to 0.5. So basically, as you change the angle of attack, you're changing CL, right? So yeah, so if you pitch the airfoil at whatever angle of attack, so that CL is equal to this, what is the center of lift? And if you pitch at another angle of attack with CL equal to 0.5, what is the center of lift? And the question is, are they stable? I just talk about like, if the center of lift moves towards the tail, as you increase CL, it's going to be stable because it's nose down. If as you increase CL, the center of lift shifts towards the nose, then it's unstable because it'll be pitched further nose up, right? And then like also do this for the negative CL. The question is, if you fly the airplane upside down, are they stable? And third question is, okay, if I have both a main wing and a horizontal tail of the same chord, same span, and the leading edge is one chord downstream of the trailing edge, so answer the same questions. All right.
This was still like the first one, the non-symmetrical one.
It's always like,
Yeah.
so as we increase the CM increases, the distance goes closer to the nose.
Yes, unstable.
Yeah, unstable. That's right. Yeah, so you calculated these numbers. Does it mean stable or unstable?
Yeah.
As you increase, it seems unstable. Yeah, because it's going closer to the.
Going closer to the nose. That's right. So it's unstable.
Thank you.
Any questions?
Not yet.
Nice colors.
We're going to be calculating the location of the center of lift using CM.
Yes.
Right.
Yes.
But I wanted to, I actually just wanted to ask this clarifying question before. If we didn't have the CM, how do we go about doing that? Like, I guess one solution is to integrate or find discrete sections.
Yeah,
and add
yeah.
them together
I mean,
to
that's how Xfoil does that.
Okay.
I think that's.
by hand though. Is there any other way we could do it on a test, for example? If we didn't have the CM.
Yeah, on the test, I wouldn't. I wouldn't give a problem that would require you to do numerical integration.
Okay.
That'll take too much calculations.
Okay.
But if it's just the area, right? Then you can use like a triangular approximation or something. Then you can do it. But here to get CM, you have to integrate the difference multiplied with the lag, right? So that's I think too much calculation for a quiz.
Yeah, that makes sense.
Yeah, so I wouldn't ask you to actually approximate the CL with a graph like that.
Like the CL location. Okay, yeah.
Yeah. I'm always going to give you like the CM for some angle,
Okay,
and
that
then
makes
you can just use the same CM for other angles.
Okay. And also, just because I think I've forgotten, for a symmetric airfoil, can we always pretty much assume that the center of lift is on the forward?
Yes,
Okay.
yes. According to thin airfoil theory, that's always the case.
Okay. Thank you.
Yeah.
It actually, yeah. So that's unstable. Yeah, that's unstable. And then this one, cheat question. So when the center of lift increases, do we want, when the coefficient of lift increases, we want the center of lift to move back? That would be a representation of stability.
Yeah.
How much does it have to move back to be stable?
Well, as long as it moves back, it's stable.
Okay.
Yeah.
As long as
If it doesn't move at all, it's neutrally stable.
Oh, okay. So that one would be neutrally stable.
Yeah, that'll be neutrally stable. Yeah.
Okay. And it's basically like the CM doesn't change with the increase in CL because it's at the same angle of attack.
Yes. It changes. No, the angle of attack changes. Otherwise, you wouldn't get a change in CL.
I see.
But thin airfoil theory tells you that CM
CM
doesn't change as you change angle of attack.
I got it. Thanks.
Yeah. Very good.
I think we're a little. Is it like past 50? It becomes unstable.
So as long as the center of lift moves towards the leading edge, as you increase CL, it's going to be unstable. So here you can see it's unstable just because. This is a. Yeah, so as you increase CL, the center of lift shifts from
0.5 to 0.46.
exactly from here to here, right? It's moving towards which direction?
Towards the leading edge.
Towards the leading edge. That's unstable. So stable or unstable cannot be assessed from a single angle of attack or single lift coefficient.
Okay.
You have to see the trend. Okay, so when you increase the angle of attack, which also means you increase the lift coefficient.
4412 is unstable, but
Yeah.
0012 is
012 is neutrally stable.
Neutrally stable, yeah.
Yeah, because it doesn't change exactly. Sorry.
When we're talking about like increasing CL, that would go like for the magnitude of it, right? Not like from a,
Yes.
okay.
When you're flying backwards, you actually want negative CL,
Yeah.
right? Yeah.
Okay. Cool. So we're just like for number 3, we're putting them like on next, like on top of each other, like.
No, one behind another.
Oh.
So the
okay.
leading edge of the downstream one is one chord downstream of the trailing edge of the front one. There is one chord length between
them. Okay.
Yeah.
Okay.
Yeah, exactly. Yes.
Nice.
So, could you average these?
This is 0, and obviously, I think this is the point of having like a horizontal split.
Okay, so the third question, you actually have to use multiple things from thin airfoil theory, right?
Okay.
Yeah. Like when I say, okay, average CL 0.4, what is going to be the CL of each one? Well, actually, it doesn't really matter, but like, yeah, if you can.
Can I ask a question?
Yeah.
How do you define the center of lift if you have two airfoils? Like two airfoils? Do you think?
Yeah. Okay. That's a good question. So, if you can calculate, so the center of lift is a point around which the total moment is going to be 0.
Oh, okay.
Right. So, for example, if both airfoils are Nakata 12 are symmetric airfoils, then both are going to be both lift are going to be at the quarter chord, right? So if you so then you have to compute at which point the combined moment is going to be 0. It'll be right over here, right? At like 1/4 chord, the downstream of the trailing edge of the first airfoil, because the distance is going to be the same and the lift force are the same. So this is going to be the center of lift. But now this airfoil is not symmetric, right? And they're going to be producing different lift and at different center of lifts. So where would you be? Yeah. So around the where would you get 0 moment?
Okay. You find both of them and then the ratio of the things.
Yeah, one way to do that is if you can calculate what is the moment around this quarter chord, okay, and you can also calculate what is the moment of the lift vector from the downstream ones, because it's exactly 2c, right? Okay, so you can do. We used to have this, right?
Yes.
Okay, but now, if you know, so the moment, in this calculation, right, the moment is only from this airfoil and the lift is only from this airfoil. So instead, if you have the moment, if you have the lift from both airfoils and the moment from both airfoils, then you can still use the same calculation. So basically CL1 plus CL2, and you have CM1 plus not the CM2, because the CM2 is measured against this point and is 0. So what if you measure the moment of this lift around this point?
2C plus something else.
Yeah, so that's actually 2 times CL2, right? 2 is the 2C.
Oh, okay.
Yeah,
C is
because the moments are always non-dimensionalized with respect to the chord, right? Okay, so that's how you would calculate actually minus because yeah, this actually creates a no star moment.
Can I also ask a question for 2?
Yeah,
So we found these things, like these numbers,
yeah.
but I was thinking like if we have an airfoil and we like this we got that this is unstable in the first one.
Yeah,
So like if we have something like this, it's going to become unstable, right?
yeah,
If we have like the opposite thing,
yeah.
what if this happens? Will it not go unstable in this direction?
Okay, so if you have an airfoil like that, right? So it needs to be producing lift in this direction for you to be flying, right? So your center of gravity. So here, if you're flying this airfoil, your center of gravity has to be placed over here, like around 0.5. For this to fly at a steady state, your center of gravity is going to be approximately here. So it's basically two different.
Okay, yeah.
Two different
I was
scenarios.
thinking lift. Okay, yeah. That one.
All right.
Chi-Chi.
Yeah.
Question. So we're trying to find the center of lift here, and we want to take the 0.45 and the 0.5 cases.
Yeah.
We average those out, and we get the center of lift to be half chord here. Then we average the 2 cases out, and we get center of lift to be a quarter chord here. And then we have this location is 0.5C, and then this is 2.25C away from the very front. And then we average the 2 values together, and we get like 1.375C. So we get the center of lift to be like right here.
Yeah. 1 second.
Sure.
Actually, these are going to have different magnitude of lift.
That's what I was thinking. There's like some weight, right?
Yeah, so you can't just average them, because I mean average them assumes they are producing the same amount of lift.
Right.
And for example, if you have 0 angle of attack, this is not creating any lift. This is creating a pretty significant lift. So you can't just average them.
Okay.
Yeah.
So we have to.
Yeah. Okay. Maybe. Okay. So I see everybody got question 1 and 2 correct, and for question 3, I think it's a little bit hard. So I'm going to just talk about how we solve question like that. All right. So for question 1 and 2, I think almost everybody just plugged in the center of lift. So x, let's say center of lift is equal to a quarter chord. I mean everything times c minus cm over cl, right? Times the chord. Okay, but for question 3, it's not really obvious we should use this or not, right? Actually, we cannot, because what is this quarter? This quarter represents the location around which we are measuring the center of moment, right? Okay, so if you just ignore this quarter, just the minus cm over cl times c, that's actually the center of lift relative to the quarter chord, and we add this quarter chord so that it is a location relative to the leading edge. Now, if you have 2 airfoils, you have 2 CMs, and these 2 CMs are measured around the different locations. It is, I mean, like, I don't know, like when you do mechanics, is it okay to add the moment around the 2 different locations and call it the moment around something? And you can't, right? So basically you have to convert things around the same center and then at the moments. So for example, in this case, let's look at both wings. And we need to figure out, for example, let's just choose the front wing, the quarter chord of the front wing, and calculate what is the moment around that. So the moment around that is, of course, the cm of the, let's say this is airfoil 1, this is airfoil 2. So cm 1 plus whatever lift, so this is the lift created by the second airfoil, times the lag, right, between the center of lift of the second airfoil and whatever point we're measuring the moment around. So, and by the way, this is a nose down moment, so should be minus CL2 times the lag, which is 2C, right? And remember, like for moments, we are non-dimensionalized by an additional chord length compared to the lift coefficient. So we divide it by C. So this is CL2 times 2C divided by C. So the total moment we get is CM1 minus 2 times CL2. So that's the total moment around the front quarter chord. Okay, and then to find out the center of lift, we actually use the same way we derived this formula. So it'll be the XC is going to be a quarter, which is basically measured around the leading edge of the front airfoil, minus CM1 minus 2CL2, so that's the total moment, divided by the total lift, CL1 plus CL2. So that's how we are going to be figuring out where the center of lift is relative to the leading edge of the front wing. All right. Why did I divide by C? Yeah, good question. Because CL is defined as the lift divided by half rho U squared and divided by usually the planform area. Cm is defined as the moment around the quarter chord divided by the same thing, half rho U squared and the same reference area, and again the chord. That's the only way to make the moment also non-dimensional, right? Because the moment has different unit as force. So yeah, so basically to get it in the same non-dimensional unit, you need to divide the CL by another C to get. You need to basically multiply the lift by its lag length, divided by the non-dimensional things to get the CL, and then divide by additional C to get a moment. To get the same non-dimensionalization as the moment. All right. Okay. All right. So I can talk more in the beginning of the next lecture about this, just to answer more questions about this, because I think I derived this very quickly. So yeah. So see you on Friday. And after this, we are going to start talk about the viscous flows. Now the flow may separate, the wing may stall. All right.